you to the 13th inaugural lecture of the inaugural lecture series. Today, the inaugural lecture will be delivered by Professor Lidula Nilakshi. So, to introduce the inaugural lecturer for the day, I would like to warmly welcome Professor Anura, Head of Department of Electrical Engineering, University of Engineering, University of Lidula. Over to you, sir.
Good afternoon. Dear Chancellor, Vice Chancellor, Deputy Vice Chancellor, Deans of the faculties, Senior Professors, Senior Lecturers and Lecturers, members of the public who have joined us this afternoon, students, ladies and gentlemen. It's a great pleasure for me to introduce Professor Lidula Nilakshi, who is a colleague of mine working at Department of Electrical Engineering, University of Nilakshi. She graduated with BSc degree in Electrical Engineering with first class honors in the year 2002 from University of Nilakshi, Sri Lanka. Soon after graduation, she joined the Department of Electrical Engineering, University of Nilakshi, as a temporary lecturer. She received the Asian Development Bank full scholarship and completed the Master of Science in Electrical Engineering in 2004 from University of Nilakshi. With the receipt of AIT and the Government of France full scholarship, she completed her Master of Engineering degree in Electrical Power Systems Management in 2006 from the Asian Institute of Technology, AIT, Bangkok. She was nominated as the best woman candidate from the energy field of studies. She completed her PhD in Electrical Engineering in 2012 from University of Manitoba, Canada. Lidula has received several merit scholarships while pursuing her PhD, which includes University of Manitoba Graduate Fellowship, Manitoba Graduate Scholarship, and full Industrial Research Fund from Manitoba Hydro, Canada. After successfully completing her doctoral studies, she joined the University of Nilakshi as a senior lecturer in September 2002. She was promoted to the grade of professor in year 2020. She is a chartered electrical engineer and a member of IESL and a member of IEEE. Her research interests include microgrids, distributed generation, renewable energy systems, and power system modeling, stability, and protection. Having an H index of 14 and I-10 index of 19 with more than 1,800 citations for research publications, Lidula has received several awards, which include the President's Award in 2014 for scientific publications and the University of Nilakshi Outstanding Research Performance Award continuously from 2014 to 2021. Lidula has been serving the University of Nilakshi, other universities, and the country in different capacities to uplift the higher education sector and the power sector in Sri Lanka. She is an asset to Department of Electrical Engineering and University of Nilakshi. Ladies and gentlemen, with that, I present Professor Lidula Nilakshi to do her inaugural lecture on the theme Microgrids as a cornerstone for renewable energy future.
Good afternoon, everyone. Thank you very much, Professor Anura, for introducing me. I would like to warmly welcome all of you here today for my inaugural lecture. I have my dear lecturers, my loving people, my friends, all joined some online also. So it's a great pleasure and it's a great honor for me to talk to you today, giving my inaugural lecture today. So I am very much grateful to all of you. So let me start. I'm going to talk about microgrids as a cornerstone of the renewable energy future for enhancing reliability and power quality through intelligent integration. So I'm going to use my research in delivering this lecture. Now, this shows the demand curve of Sri Lanka, which is showing throughout the years after 2020. You can see that there's a growing as expected because with the population growth and with the needs, growth of the needs, we can expect an increase in the demand. And by 2020, it is around 2,600, and of course, we have more than 2,600 megawatt demand by now. And you can see we have capacity more than 4,000 megawatts. So why are we experiencing these power cuts while our system is not that reliable? So if you look at the energy mix here, you can see we are relying mostly on very few energy types, energy resources here, right? So the problem is now, although we have the required capacity, in case if there's scarcity in any one of these type of resources, for example, if you are in a drought period, we will not have enough hydro to serve the demand. And in an economic crisis, we may not have coal available to supply the required energy demand. So that problem is there. So what is the solution? Now, what are the available resources we can go for? We are talking about 70%, we have a proposal to go for 70% renewable energy resources, that is new renewable technologies using solar and wind type. Even now, if we consider the total renewable generation capacity, we have more than 50%. And if we are looking for increasing new renewable generation, is there a problem? Actually, we did a study this is done with one of my part-time MSc students. Actually, we did it in 2018. So we were looking at the long-term generation expansion plan from 2018 to 2037. So at that time, when we look at the 2030 system, the proposed system, we had pump storage systems and we had some pouring back. So in this study, we considered those. I'm showing only one scenario here, hydro maximum day peak scenario. You can see we have about 80% renewables here, including major hydro. So in that situation, if there's a tripping of one plant, N-1 contingency is considered here, tripping of one plant under a situation where solar is ramping down, the system could come back and be stable. The red line shows the system with existing load shedding scheme, that is with the existing system as proposed to 2030. And actually we did this study for proposing network upgrades, introducing a dynamic load shedding scheme. With that, we were able to get better results, but even having this enough system inertia, like having the pump storage and sample also in there, if we trip about 30% of generation, that is losing the coal power plant and losing 50% of wind generation is considered in this example. In that case, if we use the existing load shedding scheme, the system goes into a blackout according to our results. But if you go with new technologies that we propose, system could come back. My point here is that if you are going to integrate new renewable technologies, usually which are connected using power electronic interfaces, we don't have enough inertia in the system. So we must look for upgrading the network. We must plan, we must do studies and do the integration. So that is one point I want to make from this research. So now let me introduce the microgrid concept and its importance. So what we try to do with the conventional power system is that to balance the load using some central generation, we are using some tie lines to supply the demand to the consumers. So if there's some contingency, like if we trip a tie line or if we trip a large generator in the system, you can understand that we may experience a total blackout or maybe brownout here. But if we could distribute the load locally using the renewable generation, in that case, the beauty here in the microgrid concept comes here, right? We can isolate from the system. If there's a problem in the main system, we can get isolated from the main system and operate as independent systems with full control. So this is the beauty I wanted to highlight in the concept of microgrid. Right. So let me define a microgrid. Microgrid is an entity. It is actually part of the power system which will have energy sources including energy storage devices, and it has loads. So it is a part of the power system, but it has full control to operate as a grid connected entity or an autonomous power island. So it has an identified boundary. Now, since it can operate connected to the grid and as a power island, you should understand that the control must be changed. When it is operating connected to the grid, the frequency is controlled by the grid. But when it is islanded, there should be a grid forming unit, a source, to control the frequency and voltage. So with that understanding, let me go further. Now, I was telling the microgrids, we can use the local energy resources. I will take one example here. When we take solar PV, now we have a problem with solar, right? Now you have experienced it pretty much in Sri Lanka. Although we have rooftop solar available at our home, when there's a power outage, we can't use it, right? Although the solar rooftop is there, we can't use that generated energy. That is coming with actually the standards which has been implemented so far. So IEEE 1547 previous standard, it was specifying to trip off these distributed generators, the generators connected to the distribution system within 2 seconds if the grid is not available. That is actually for the security purposes, security and protection requirements, because the dispatcher doesn't know whether these generator stations are there or not. So that is for security. But with the new standard IEEE 1547.4 2011, it allows the connection of these solar PV system in the system itself as controllable entities. We must have frequency and voltage control, but if not, like if we were operating as grid tie inverters, they cannot control your frequency and voltage. So it is not really safe to use like that. But when we go into microgrid concept, we can use solar PV. And another condition is that sun doesn't always shine, right? So we know that we have the sunshine at daytime, but when we need electricity more at night time, we don't have that. So the present systems, the grid tie inverters, the solar energy we don't have at night. So with this microgrid concept, we will have the control, we'll have energy storages available, so we can go for optimized use of solar generation. And when we look at the other property of this solar generation, it is intermittent in nature, so it can cause instability issues with this intermittency. But having the controlled energy entity in a microgrid, that is with the energy storage and all, we can control the intermittency and we can use it for like a stable system without any fear. And also, dispatching is complex if we go for natural integration of solar PV without going into microgrids, because it is really difficult and we need high mathematical optimization techniques with forecasting if we go for direct dispatch of intermittent renewable energy sources, including solar. But when we go into microgrid concept, microgrid can be considered as a generator or a load by the dispatcher, because we can specify this is what we need, and that can be controlled within the microgrid. And of course, PV panels are expensive, we know, but with the microgrid concept, it becomes a credit-worthy customer. We can go for low-cost financing. Now, it is same with other type of renewable sources. So you can understand microgrid supports integrating new renewable technologies. So what are the benefits we have? We can get increased reliability. So especially at disaster conditions, we can get separate from the system and operate. And we have improved energy security. We can integrate different types of energy resources, and we can get enhanced sustainability because we can integrate renewable energy technologies, so the carbon footprint will go down, and it is cost effective. It's not like augmenting the conventional power system. We are improving it locally. And most of all, we have increased control for the consumer. Now you can see there was a tariff hike, but we couldn't do anything. But if we were in a microgrid, we can make demands. It can easily go into a market structure. So the markets can be easily developed with microgrid concept, and demand side management techniques can be implemented. It's not like increasing the tariff in ad hoc manner. Like this can be used to not only to recover the cost, but also for managing the demand. So if we can implement time of use tariff like things, it can be done easily within a microgrids because it is local, small community. So I think you can understand the benefits of microgrids when we go into future power systems. Now let me go more into details of microgrids. In the IEEE 1547.4/2011 standard, it has defined microgrids based on location and boundaries. Now, the University of Moratuwa microgrid, what we have here is a facility island. It's a facility island. And the systems you have now at your homes, you have solar home systems. So they are kind of nanogrids. So it is not shown here. These are microgrids. Now, you can see there are some other microgrid classifications like lateral islands, circuit islands, substation islands, secondary islands. Now, why I'm describing this is that when we consider facility islands, yes, application-wise, it is good, but that really doesn't share the resources. Okay, so like it is better than having solar home systems. Now, if we design microgrids, when we do that, we usually design it to be self-sustained also. And another thing is that we mostly go with energy storage system. So instead of going for facility island or solar home system, if we can go as circuit islands or substation islands, we can share the energy among the community. So, another thing is that when we go for facility islands, the system is little weaker. The power quality is little low. Now, microgrid concept, it should be able to disconnect from the system, operate, and when the system is bad, it must resynchronize from the system. We also experienced this with our University of Moratua Microgrid as well. So resynchronization back is not that easy because the voltages are not at high quality. So resynchronization problem was there. But if we go to the substation level or feeder level as lateral islands, that kind of problems will not be there. So my suggestion is that we should go for resource sharing and improved power quality ideas going into lateral islands and substation islands than putting up small solar home systems and facility islands here. So this is coming from my research ideas. So this is research experience. So I suggest that as one of the possible situations. And also, we can classify the microgrids based on the voltage, and that is from the architecture. So we have AC microgrids, DC microgrids, and hybrid microgrids. So these applications, these depend on the application requirement. So AC microgrids, if we have mostly AC loads available, we can go for AC microgrids. DC microgrids are for applications like data centers or maybe ships. In such systems, we have more DC sources and DC loads. So we can reduce the number of conversion stages in such DC microgrids. And the hybrid microgrids, it's a special microgrid where we have an AC bus and a DC bus, and this would be an expensive type of design of microgrid, and this is good for systems where we are looking for very high power quality. They are interconnected using systems, so the conversion stages are very low and power quality would be very high. So I will share some of my research outcomes with you to understand this. Okay, so I think you have some background idea about microgrids now. Now I'm going to show you how I have used it in enhancing reliability and power quality through intelligent integration. So this is the conventional distribution system. When we have distributed generators, small scale generators connected to the distribution system, now the system has changed. It has become an active system where there can be reverse power flow. So that is why the previous standards didn't want the DGs to operate when there's a system loss. Now with the microgrids concept coming in, the standards have set up, we can allow this power islanding. So as I told, we have to let the system control the frequency and voltage when it is connected to the grid, and when islanded, there should be a source where it can form the grid, and others may be following and feeding. So to do that, we need some kind of islanding detection technique. And also, with these mode changes, we need energy management techniques, control and to maintain the stability of the system. There must be seamless transition, smooth transition should be done. It's not that we are starting from black. Start is not not an option in this microgrid concept. So we are switching in and out from the grid smoothly. And also prediction is another aspect of researching this. So I was focusing my research in this, and I have selected very few research to show you and share the experience. Right, let me take my part of my PhD work first. This is an AC microgrid where there is no energy storage but a diesel generator. So islanding detection, fast islanding detection is really important in such a system because they are operating in inertia. So with that, we looked at possibility of detecting the islanding event, that is when we disconnect from the main grid. To identify that, since we were looking at a fast system, we looked at the transients generating at the disconnection point. So at the disconnection, so we looked at the voltage and current waveforms at the DG. This is a passive technique where we do not need any communication. So in that, when we look at the waveforms, the original waveforms at islanding and other non-islanding transient events like force and load switching, they were almost alike. It cannot be like most of the events, they look alike. They cannot be identified as islanding or non-islanding. But when we do some signal processing, we were able to see that there's a unique signature in these. So our hypothesis was on that, to detect this unique signature happening at the islanding situation. So we extracted the required features and then used a classifier. The decision tree classifier was used after some studies with other type of classifiers at that time. So we were able to get very good results from this compared to other techniques, passive techniques. With 99% confidence, we got more than 95% accuracy in this. When we compare with other passive techniques like voltage and voltage vector shift and rate of change of frequency at different settings, you can see the accuracies, and also the response time was less than 50 milliseconds. Other types were taking longer time, even if they're at lower settings sometimes. So it is very important for microgrid to change its control, so such performance is very acceptable. And another good observation of my proposed proposed relay is that this non-detection zone was 0. Non-detection zone means the relay cannot detect it, because now I told usually the microgrids are designed to be self-sufficient. So at the time of disconnection from the grid, the power imbalance is near 0. So these other passive techniques can fail to detect at that time. So we call it as non-detection zone, and the proposed method is not depending on the power imbalance. So such systems are very good for application in microgrids. And we don't need any communication because the measurements are done at the generator itself. So that is avoided. Now in our monitor microgrid, we are having a voltage and frequency measurements. After that, the breaker signal is given as a communication signal to the main controller, because the central control is used. So depending on different criteria, we can select the islanding detection technique, but fast detection is always important. So this is one of the things that we can do more research. And then I told it is very important to look at the energy management in developing microgrids. So this shows another research by one of my MS students who worked on a DC microgrid, low voltage DC microgrid, and it is connected to single phase. And in this case, what I wanted to highlight is that since we are having different modes of operation in a microgrid connected to the grid, disconnected like that, and in transition, we can have transients. We have to consider all modes of operation in designing the energy management. Not only that, we have to look at the constraints. When we look at the constraints, one of the constraints I can highlight here, when we have energy storage system, we have state of charge levels. So safe operating levels are there. We have to be mindful to what level we are charging and to what level we are discharging. So these must be considered in our energy management. And also, I told that we might have to go for solar curtailment. I think I mentioned. So this is giving one of the examples here. When we were island, like say that microgrid is islanded and the battery is fully charged, at that time we will have to curtail the solar PV. So if we have like resource sharing, we could have used that solar energy without curtailing that. And if we have a system islanded and if we don't have enough solar, then we have to go for load shedding. Such situations must be considered in designing the energy management, and in this case we just have to control the voltage, but if we have AC microgrids, we have to control the frequency as well. So all these conditions must be looked at when we are designing and developing microgrids. So in this case, we were able to get stable output in the system. And this is another research done by my first MPhil student, and I'm thankful to all my students for their work. And in this case, again, it's a DC microgrid kind of application, kind of like for a data center. So in this, we try to develop a technique to detect faults and classify them. It is very important because now with the DC system, we don't have much information, we don't have frequency there. So it is the voltage and current parameters we have. So in that case, having the capacitor banks, capacitor links available, we used again the transient situation in identifying the faults, and we trained a neural network here to detect and classify the faults. And there we developed two types of relays, one with primary protection only and the other with primary and backup protection. So in this case also, now this shows the process of detection, one for fault situation and another for a load switching situation, both giving transients, and the results processing in the form is shown here. We were able to get very high accuracy for the both types of relays. Nearly 99% accuracy was achieved. These studies were done with huge number of data. So that is another thing. And here I want to talk about hybrid microgrids. This is again from one of my MSc students. And as I told, hybrid microgrids are expensive. So in hybrid microgrids, we have to go from the design level. At the very beginning, we have to plan that we are going for a hybrid microgrid type. So this is an AC DC hybrid microgrid where we use solid state transformer. So it is with galvanic isolation also. And for the study purpose, we use an existing system. We selected one feeder from the area, and we studied what happens if we had an AC-DC microgrid instead. We did the study like that. So when we look at the power quality that we received, you can see how the voltage regulation has happened. It shows the existing system and the proposed system results. First one shows the voltage at different bus bars, and this is the total demand distortion, and this shows the voltage harmonics DHD of voltage, and this is for DC injection. You can see even though the present system also not violating the voltage harmonics, how the harmonics have reduced, and the total demand distortion, it has reduced very much. Voltage is highly regulated so that we can integrate more renewable generation in such a system, and that depends on the capacity of the transformer, and with that, this is a very good system, and without any DC injection also, for a application where we are demanding for very high quality power, this would be a very good application. So I would like to now go into something that I am doing right now with one of my PhD students. We are working on this right now, actually. We are looking at microgrid clusters. So in this case, what we try to do is that sharing the resources in a enhanced manner. We want to integrate more renewable into the system. So in this study, we derived the networked microgrid from the Colombo City network. Actually, I did a previous study with one of my MSc students looking at creating a ring microgrid in Colombo City network, and we saw the possibility of creating the ring microgrid, and then we went on to studying ring connected microgrid cluster. It is network microgrid. Instead of operating several microgrids separately, in this case, we can share the energy. We can share, like we can integrate more solar PV without making it self-sufficient. We can integrate more renewable into the system and share with other microgrids and the network, so that we can get high energy use and utilize the renewable energy in a very good manner. So in this, we have come up to a level where we have developed a very complex energy management, very good energy management, and it is operating really well. And I'm very thankful for my student too. I believe I have found the best student to do this. And next, we are going to look at resynchronization and protection design in this, which will be kind of complex, but we are working on it, and I'm excited to get the outcome of this research. Yes, so that's what I wanted to share with you all today. I believe you got an idea about microgrid, which is a broad definition of a small power system, and it has the benefits, including high reliability, high efficiency, improved power quality, and it allows increased integration of renewables. And there are challenges, and we are working on to solve these challenges in the areas of biological detection, control, and energy management and protection. So that is for today from my research, and I'm really thankful to all of you here. It's a great pleasure, and I'm really honored once again. It's heartfelt feeling for me right now. Yeah, thank you very much, all of you who have joined online too. I know all my lecturers are there, and my friends and loved ones. Thank you very much.
Thank you so much, Professor Lidula and Nilakshi for that illuminating lecture on using microgrids as a renewable energy source. Now, I would like to warmly welcome Professor Udyanka Hemapala, the Dean, Faculty of Engineering, University of Moradua, to give away the token of appreciation to today's inaugural lecturer, Professor Lidula Nilakshi. Over to you, sir. Thank you, sir. A warm thank you to everyone who joined with us today online via Zoom and here physically at the Department of Graduate Studies. Before adjourning, I would like to acknowledge and thank our sponsors, event sponsor Cargills Private Limited, and the print media sponsor Daily FT, and the Sri Lankan scientists for being our social media sponsor for today's event. Thank you so much and have a nice day.